Hi, so now we move into a different type of test called test for homogeneity. And essentially, it's doing the same test as the previous section of testing for independence, but instead with proportions. Since we're testing whether variables in the previous section were independent, we really can't use that same approach with proportions because it's a proportion, right? It's not, doesn't have any units, it's just a proportion of, so it's a quotient. And so then we call it, well, if these proportions are like percentages, then we can't use the same exact, but we can use proportions and then have see if there's homogeneity, meaning each proportion is different than the other. So essentially, it's independence within proportions, except we call it the test for homogeneity. So here we could see that in a chi-square test for homogeneity of proportions, we test whether the different populations have the same proportion of individuals with some characteristic. So essentially, we want to make sure that we're testing whether all the proportions of the population are the same or are they different. Prior in chapter 10, we only could test two proportions, remember? And then chapter 9 was one. How do we test at least three or more, right? The test for homogeneity. So we're just doing the same kind of test that we were doing in chapter 9 and 10 with proportions, except now we just have more samples, that's all. So let's just take a look at the example. Um, oh, oh, so here, what's a nice thing that we should note is that we use exactly the same method as in 11.3, meaning everything's the same. We have a chi-squared test in the calculator, and then you're going to use a matrix. So it's nice because even though we're essentially trying to try a different test with a different parameter, it's really essentially the same method and the same test, which is really nice. Okay, so let's go ahead and take a look at the example. The following question was asked of a random sample of individuals in 1992, 2002, and 2008. Would you tell me if you feel being a teacher is an occupation of great prestige? The below presents the results of the survey. So by row, we have the response, and the columns are the years. So from each year to each year, did the proportion of teachers who answered yes or no change? Like was it actually different from 92 to 2002? Well, maybe more technology has come out from 92 to 2002 and they felt they could do a lot more and they felt it was a more prestige occupation. So we're looking for a response by years and if those proportions change throughout the years. Okay, so let's test the claim that the proportion of individuals, so we're going to test a claim that the proportion of individuals that feel being a teacher is an occupation of every great prestige is the same for each year. So it's going to be, we have to be careful what we state our claim is. We have a fixed, null, and an alternative, but one of those have to be the claim. So let's go ahead and set that up. Okay, so step one would be to set up the null and alternative. So the null and alternative here are whether the proportion of each year that it was surveyed, so we could call it, go ahead and maybe P1, P2, and P3, right? So remember, the null is status quo, so that means that the proportion wasn't different from each year, right? That means the alternative would mean that at least one of the proportions is different. Now, me do it in a different color, maybe green. It says the claim is blah, 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 is the same each year. So the same means not that one of them is different, but they're equal. So the claim here, and once again, is our null hypothesis. Okay. Step 2, identify the alpha. So the alpha they give us is 1%. And step 3 is going to be calculating the expected counts. So calculate E sub I. And then again, we're going to do that on the calculator. Part B is when verifying those preliminary results. So we just have to make sure that all expected counts are greater than or equal to 1 and no more than 20% of expected counts is less than 5. And we're going to have to determine this from the calculator. Okay, and then part C would be the chi-squared test statistic, which we will also get from the calculator. And then the last piece would be, or in the calculator would be step 4, which is the p-value. So notice a lot of this is going to be put observed in matrix. So a lot of these verifications are going to be within the calculator. So let's go ahead and do that. So let's go to our calculator. Let's go to second x inverse, which gives us the matrix. And let's go ahead and enter in C matrix. So I have something in A and B. So I'm going to go ahead and go to edit. And go to C, which is an empty matrix, and put the observed. Notice D is also empty, so I'm going to go ahead and use that for my expected when I put it in the chi-square test. Okay, so let me go ahead and do C. Notice in this case I do have 2 rows and 3 columns. And sure enough, that's what pops up here. So yes, in 1992 was 418. In 2002 it was 479. In 2008 it was 525. In 1992 the no's were 602. Then 541. And 485. Okay, so since the test is going to be the same as in the previous section, which is chi-squared, let's go ahead and do that. Let's go to second test chi-squared, which is C. Enter. And my observed is not A anymore, right? My observed is that matrix C. So let me grab it. I would just go back to the matrix menu. I would go second X inverse. And from the names, I would go down and select the one that was observed, so 3. And therefore, I would have to use expected as an empty matrix. So let me go ahead and hit second. X inverse goes to the matrix menu, go to the names and select an empty one, which would be 4D. Okay, so let me go ahead and calculate it. And let me drag this over. So at that point, the moment I hit calculate, it automatically ran the numbers for the expected counts. So let's go back and hit stat, test, and go back to chi-square. And let's draw it. The p-value is pretty small, so when it draws, you probably won't, it'll be like, you probably won't see it, right? And notice again, like the p-value is going to appear to be 0 because that chi-squared is way to the right. Okay, but we still have to satisfy these B1 and 2, right? So let's go ahead and grab the expected matrix from our calculator. So I would hit second, X inverse, and notice D is filled in, 2 by 3. Those are the expected counts. So let me hit edit. And let me go down to 4 and hit enter. And that way you can view all the expected counts for each category. And I'm going to go ahead and drag this over. I'll do blue. So so we did that in the calculator, right? We calculated expected counts. All expected counts are greater than or equal to 1, so we can see that they're quite large. So definitely, and no more than 20% of expected counts can be less than 5, and none are less than 5, so we definitely match that. Our chi-squared test statistic is 24.74. And then notice that once again, the p-value has given us 0 on the graph, but it gives us some digits in the calculate menu. So if you want to see some digits, I would definitely use the calculate menu, but draw still works because it's still pretty small. It just depends how far you want to round your p-value. So here, the p-value is equal to 0.000042, and the alpha we wanted was 0.01, and we can see that that is much smaller than the alpha. So here, if I grabbed another sample of years to ask whether teachers felt their job was a prestigious occupation, this p-value implies that that probability would be highly unlikely to be the same, and therefore we have to reject the null. But recall that if we reject the null, what else are we rejecting? Well, our claim was the null hypothesis. We rejected the null, and therefore we have to reject the claim. And so there is not enough evidence to support the claim. So step 5 would be there that the response proportion is the same for each year.